Hello everyone, it's Peter from Not Just a Geek again. Today, I'd like to discuss where Earth gets the majority of its energy from, and how you can maximise its use in your daily life. As we all know, the Sun is our primary source of energy. It sits roughly 148 million kilometres away and continuously generates energy through nuclear fusion, which is then radiated towards the Earth. This energy comes in the form of the electromagnetic spectrum, and the heat primarily comes through the infrared light, which helps to warm the planet up. But the question is, how much energy do we get from this? Well, solar irradiance at the top of Earth's atmosphere is roughly 1,361 watts per metre squared, and this remains relatively constant. However, on Earth's surface, this value drops to about 1 kilowatt per metre squared on a clear day, and there's much more variability depending on location on the planet's surface and weather conditions. As we stand in the sun's path, we can feel its warmth. But how can we take advantage of this energy to reduce our energy bills and increase home comfort? One simple and cost-effective method is to utilise the windows in our homes. When the sun shines through a window, it heats up the fabric of the room, which then heats the air. However, windows are not perfect insulators, so when the sun is not shining through them, they lose heat. In fact, on a clear evening, windows can even radiate heat into space. Useful in the middle of summer, less so during winter. To offset this, we can use blinds and curtains to insulate our homes. But the question then arises, when should we open and close them? Should we open and close them? And this is where Forecast.Solar comes in. This is a website which provides a REST-based API, that is, a way for computers to view the website, which can be used to forecast the generation of a solar panel, or solar array. The data is based on historic irradiance data combined with weather forecasting, and given that we know the maximum heat gain on Earth's surface from a solar panel is 1 kilowatt per metre squared, we can model a window as a 1 kilowatt solar panel and then multiply any output by the area of glazing. The first two parameters are the location details, the longitude and latitude. And in this case, we've put in the details for Paddington Bear's address in London. We've assumed that our window is mounted in a wall, and so a 90-degree angle, and that the azimuth is 0, which means it's facing south. And when we visit this page, we're given loads of text in a format called JSON, which relates to the watt-hour periods aligned with predicted generation per hour. So, for example, we don't see any data for 2 AM because there's no sunshine at that point. However, when we look at 10 AM, we see some numbers. And this is useful, but not overly usable. So I've taken this API and integrated it into Google Sheets. Here we see the same data, but in a much more readable format. Now, looking at the spreadsheet, we can see various inputs in yellow and outputs in green. We'll use Paddington Bear's address again, good old 32 Windsor Gardens in London, and as you can see, we now have some date and time data along with solar gain in these cells here. You'll note, if I change the orientation of the panels to north facing, that, with some time, all the values change as well. And that's because we've changed the direction that they're facing, so we've changed the kind of window for when we'll gain energy and how much we're forecast to gain. And our goal is to use this to work out the total solar gain or heat loss through windows in at least one orientation of the house. So, I've modelled our house as if it existed in the middle of London, which it does not. We don't have any skylights, so I've set the angle to 90 degrees, and we're south facing, so that's what we're focusing on. I've set the outdoor temperature to 7 degrees, because that's a fairly reasonable average for around this time of year, maybe a bit earlier. And I've set the target indoor temperature to 18 degrees. And these are relevant for heat loss calculations. Here you can see the windows for various rooms in the house. I've detailed the windows for our living room, cloakroom, and 2 of the bedrooms. You'll note the U value on the bedrooms is lower than the other rooms. These are older windows, literally very early 80s double glazing, and they're in an awful state and they really need replacing. But it's handy to include them because it helps us see the impact of heat loss. So, looking at room-specific results, we can see that the 27th of March is universally sunny, and so we get a net gain regardless of blind states, whether they're open or closed. However, we still have an improvement in having the blind open rather than closed, and we have an improvement again by having the blind in the optimum state. The 28th, however, is more variable. On this day, it's much more apparent the importance of using blinds and curtains. You'll note that regardless of behaviour, we have a net loss in 2 of the rooms. These are the rooms with the older double glazing and, as you can see, they have higher heat losses as a consequence. The optimum method effectively involves opening the blinds when the heat loss is less than the solar gain, and then closing them again when the solar gain has reduced below the heat loss. So, given the parameters of the property, we've concluded the heat loss will average 23.1 watts per metre squared. So whenever solar gain is above this point, we want the blinds open, and this value is obviously significantly impacted by the environment. So if we set the outside temperature to -5, the heat loss increases to 48.3 watts per metre squared, and if we set the outside temperature to 15 degrees, then the heat loss drops right down to 6.3 watts per metre squared. To explain these columns, max solar gain is the gain assuming no heat losses or refraction from the glass. The blinds open assumes blinds are open all day, daytime and nighttime. And this means that there will be some more loss at night because the blinds won't be offering any kind of insulation. When the blinds are closed, in the blinds closed state, we assume the blinds are closed all day and all night. And so again, we'll lose some of the potential gain because there's a blind shading coefficient, which will reduce the infrared gain. But at the same time, we will reduce our heat loss. And the optimum, well, we've already discussed that. If we look at the summary results here, we can see that for both days, the house as a whole has a net gain. And this is interesting because it directly correlates to our need for heating. So it's pretty obvious that we'll use less energy for heating on the 27th of March than we would for the 28th of March. And so all this data is fairly easy to compute. And so I've integrated it into Home Assistant to allow me to act on it to see what impact it has. So the graph on screen shows sensor data from Home Assistant for one of our bedrooms. The OC status is whether it thinks we should open or close the blinds. And as you can see, there is a clear link between the forecast solar gain and the indoor temperature. This room's had heating disabled for the last couple of days to help us measure this more clearly. What's interesting is that there is a clear lag between the solar gain and the increase in measured temperature, presumably because the fabric is heated by the sun and then it conducts that heat into the air, which moves around the room using convection. So, back to the first thing. How can you use this energy to help reduce your bills? Well, it'll sound pretty obvious, but open your curtains in the morning and close them at night time. And depending on the orientation of your house and the time of day and the time of year, you may want to open your curtains slightly earlier in the day or slightly later in the day. But you're probably wondering, why am I interested in this? And why I've put all this effort into it? And initially it came from a curiosity about the benefit of fitting automatic blinds. So I wanted a justification for buying a new toy. And my assumption was that having something automated might be useful. I assumed that on a day like today, it might be sunny for a few hours, then there might be a rainstorm, and then it might be sunny again, and that during the rainstorm, the level of light, or irradiance, would drop to the point where I benefit from having the blinds closed. It turns out that weather is far less significant than the sun's path through the sky. Generally, for this time of year, opening blinds at 9 AM and closing at 5 PM provides optimum results, at least for where we are in England. And so the experiment, if nothing else, took away my justification for buying fancy motors for all the blinds and curtains. However, it does offer other potential benefits in terms of home automation, especially when combined with electric heating, solar panels, and home storage batteries. All the variables calculated in the spreadsheet can be hard-coded or automatically determined through sensors in a home automation product. Therefore, it should be possible to predict how much heat will be gained through the windows on a given day. As shown in the previous graphs, I've done some early integration of this data into Home Assistant, currently just for visualizing and getting clues for when to open blinds, but I'm keen to explore more intelligent ways to use this. An obvious area is having more complete heat loss calculations to work out what heating is required for a room. If I know that the room is only going to require a few kilowatt hours of heat to bring it up to a comfortable temperature, and that in the next hour it's going to receive that from the sun, then there's no point in me artificially heating the room. All that's going to do is lead to the room becoming too warm. And so it's possible that we might be able to predict when the room is comfortable, and depending on the occupation of the house, there may be no harm in letting it be slightly less than comfortable for that 30-minute, 1 hour waiting period. Or, if we were to take our home and rotate it 90 degrees, such that the windows faced east-west, we could determine that the west part of the house might benefit from heating in the morning, where the east would have sufficient thermal energy from windows to require no heating. Or perhaps, if it's raining and cloudy in the afternoon, that we'd want to prioritise heating in the afternoon in both parts of the house, but even then with more of an emphasis on the east and the west. Or if you had solar panels on the house, you could use this data to work out what percentage of your needs could be run directly from solar or a home storage battery. At the moment, we charge our battery using an off-peak tariff, and some days we get enough sunshine that we don't need any power from the grid, other days not so much. If we could predict how much thermal heat we would need to heat our homes, along with how much solar we're likely to get for our panels, we could probably forecast whether we should be buying off-peak energy in the night and how much we should be buying. Now this video is focused on solar gain and heating because currently for us the climate is quite cool. And we're just entering spring. But this same logic inverted could apply for a warmer climate to help with cooling. This is an area I'd like to explore more, especially how much heat could be dissipated through radiative cooling on a clear night, and the impact blinds might have on that process. Maybe, just maybe, automatically opening them at right times during the night might give me the justification I need for automating my blinds and curtains and buying those unnecessary motors. So these are all areas that I plan to experiment in with my home, and if you're interested, I'd suggest you subscribe to hear about the progress I make in this area. Similarly, I'd love to hear in the comments if you have any other ways that you think this data could be used. Great, thank you, bye!